The same field planted with the same seed can produce 60% more grain, or 30% less, depending entirely on which fertilizer was applied and when. The fertilizer is not just plant food. It is the variable that separates a productive farm from a marginal one. Plants require 16 essential elements. 3 come from air and water. The other 13 must come from the soil. Of those 13, 3 are consumed in quantities large enough that soils cannot replenish them fast enough through natural cycling alone. Nitrogen, phosphorus, and potassium are the primary macronutrients. Nitrogen drives vegetative growth, and in grain crops, the protein content of the seed itself. Phosphorus drives root development and energy transfer within the plant. Potassium regulates water movement, enzyme activation, and disease resistance. A shortage of any single one creates a ceiling on yield, regardless of how well the others are supplied. This is Liebig's law of the minimum, articulated in the 1840s, and it remains the central operating principle of crop nutrition today. Urea is the most widely used nitrogen fertilizer in the world. It contains 46% nitrogen by weight, the highest concentration of any solid nitrogen source. Applied to soil, urea converts to ammonium and then to nitrate through nitrification by soil bacteria. Nitrate is highly mobile and moves directly to roots, but mobility cuts both ways. Nitrate that is not taken up within a narrow window leaches into groundwater or moves with runoff into waterways. Ammonium nitrate offers a different balance, delivering half its nitrogen as ammonium, which resists leaching, and half as immediately available nitrate. Diammonium phosphate, known as DAP, supplies both nitrogen and phosphorus in a single granule and is particularly effective at establishing root systems in the weeks after germination. These materials are chemically precise, the dose predictable, the timing manageable. This is why synthetic nitrogen accounts for roughly half of all food production globally. The efficiency of synthetic nitrogen application, the proportion of what is applied that actually ends up in the harvested crop, averages between 30 and 40% globally. The remainder is lost to leaching, volatilization as ammonia gas, or denitrification back to atmospheric nitrogen. The loss rate depends on soil texture, temperature, rainfall timing, and the specific nitrogen form used. A field with sandy soil in a wet year may lose 70% of broadcast urea before the crop can access it. Nitrogen applied too early in the season, before the crop's uptake rate is high enough to intercept it, is largely wasted. Applied too late, after the crop's critical development window, it produces no yield response. The gap between what is applied and what is used represents both an economic loss and an environmental load on the surrounding watershed. Slow-release nitrogen sources address the timing problem by extending the period over which nitrogen becomes available. Sulfur-coated urea surrounds each granule with a shell that degrades at a rate determined by soil temperature and microbial activity. Polymer-coated urea uses a resin coating that controls nitrogen diffusion directly. These products typically release nitrogen over 60 to 180 days, matching the extended uptake window of a full-season crop. In research trials, polymer-coated urea at equal nitrogen rates produces yield increases of 5 to 15%, with nitrogen loss reductions of 30% or more. The trade-off is cost. Polymer-coated urea can cost 2 to 3 times more per kilogram of nitrogen than conventional urea. For high-value crops, the answer is frequently yes. For commodity grain on price-sensitive farms, the calculation is tighter. Manure, compost, and other organic nitrogen sources work through a fundamentally different mechanism. The nitrogen in these materials is bound within organic molecules and must be mineralized by soil bacteria and fungi before the plant can use it. The rate of mineralization depends on temperature, moisture, and the carbon-to-nitrogen ratio of the material. Cattle manure at around 20 to 1 will mineralize relatively quickly. Straw at 80 to 1 will actually immobilize mineral nitrogen as microbes consume it to break down the high-carbon material. This unpredictability limits organic nitrogen management at scale, but the long-term effects on soil biology are significant. Repeated organic matter applications increase microbial diversity, improve aggregate stability, and increase the soil's ability to hold nutrient ions against leaching. Research over 10 to 20-year periods consistently shows that organically managed soils maintain their nitrogen supplying capacity with less applied fertilizer over time. Phosphorus behaves very differently from nitrogen in soil. It does not leach. It binds tightly to iron and aluminium oxides in acid soils and to calcium in alkaline soils, becoming available only slowly through root exudates and mycorrhizal fungi. Phosphorus applied in excess of crop removal accumulates in the soil. Fields with decades of phosphorus fertilization often have soil levels far above what any crop can use in a season. In these situations, reducing phosphorus application does not reduce yield, it reduces cost. The soil reservoir supplies what the crop needs. Potassium is similarly immobile, held on soil cation exchange sites and cycled more predictably. On sandier soils with low exchange capacity, potassium must be replaced systematically. On clay-rich soils, the reserve may sustain multiple seasons without application. Yield response to fertilizer follows a curve, not a straight line. The first kilogram of nitrogen applied to a deficient soil produces a large yield increase. The 10th produces a smaller one. The 30th may produce no increase, as excess nitrogen promotes vegetative growth at the expense of grain fill. The economically optimal nitrogen rate, where the cost of the next kilogram exceeds the value of the yield it produces, depends on the price ratio between fertilizer and the crop. When grain prices are high relative to nitrogen costs, the optimal rate shifts upward. When fertilizer costs spike, as they did in 2022, the same practices that were profitable at previous price ratios suddenly were not. Fertilizer choice is not just a biology decision. It is a market's decision made with imperfect information about both the soil's baseline supply and the season's weather. The fertilizer that produces the best yield is not always the one with the highest analysis number on the bag. It is the one that delivers the right nutrient in the right form at the right time, into a soil that can move it to the root.